Hey class, in today's lesson we're going to talk about shifting, reflecting, and stretching graphs, which is found in section 1.3. Our objectives are to recognize graphs of common functions, to use vertical and horizontal shifts and reflections to sketch graphs of functions, and to use non-rigid transformations to sketch graphs of functions. What you see are a summary of graphs of common functions. In the first one where it says the letter A, so right here, that's considered a constant function. And we know that it's constant because there is no change in that graph. It's just a horizontal graph. The identity function, I typically call that the parent. Oh, this stylus is terrible. Parent linear function. Okay. C is the absolute value function. D is a square root function. I usually, when we're in class, I say lift off. Okay, so that's the square root function. Below that, I can't really see. Here it is. We have the quadratic function. And a lot of times I call that the parent quadratic function. Then we also have the cubic function. And again, I call that the parent cubic function. The reason why I call them parent is because they are the basic of their function, and if you manipulate by transformations, then it's no longer the parent, but this is the basis that we always come back to reflect on. Alrighty, so vertical and horizontal shifts. Vertical shifts, they tend to take place at the end of the function. They take place at the end of the function, so you'll see a plus or minus of a number at the end of your function. However, when it's a horizontal shift, it takes place either within your parentheses or sometimes it's within your absolute value. So like x plus or minus c on the inside of your absolute value. And the one thing I always like to say, it's opposite of what you think. Okay, so if you think that if you know that you're shifting to the right, it's actually going to be a minus on the inside. However, if you shift to the left, it's going to be a plus on the inside. Okay. All right, so example 1, it says compare the graphs of each function with a graph of f of x equals x cubed. These are things that you just need to type in on your calculator to see what they look like. But as a reminder, the parent function f of x equals x cubed is a simple function like that. Okay, so what's going to happen on this first one is that it is going to shift down 1 unit. So to state it, we're going to say shifted down 1 unit. Okay. On the one on the right, h of x equals x minus 1 cubed. What happens to that one is because the x minus 1 is on the inside, we don't go in the direction of what we think, which we would think we would go to the left one. We're actually going to go to the right one. So it's going to shift to the right 1 unit. So shifted right 1 unit. Okay. All right, so in try number 1, it says compare the graph of the function k of x equals x plus 2 cubed plus 1 with the graph of f of x equals x cubed. As a reminder, the parent cubic function is here. And so essentially what's shifting is the center of it. Okay. Remember, these are our transformations, right? I'm going to put an asterisk next to the 2 because since it's within the parentheses, it's opposite of what we think. So this one is actually going to shift to the left 2, and then that plus 1 is a vertical shift up 1. So there is that shift, and so it's going to look like that. So again, it is shifted left 2 units and up 1 unit. All right, the picture looks terrible, but just go with it. So in example 2, we're finding equations from graphs. So the graph shown is a shift of the graph f of x equals x squared. So they want to find the equation for g. So we're now going to call this g of x. So this function is called g of x. They're telling you that it is a shift of the function x squared. So we just have to figure out how it shifted. Well, if I look accurately, x squared should be about right here, and I may have made it too wide, but just go with it. But it has shifted up 1, 2, 3, 4 units. So that's plus 4 up. So that would be x squared plus 4. So that's the new function. And try number 2, again, they're telling it is a shift of the graph f of x equals x squared. So again, this is still an x squared. We're now saying that this is h of x is what we're looking for. They're asking for us to write it in terms of h. And again, we focus on where it started from. It started from here at the origin, right? It started at the origin. But look, it is now shifted. If I find the vertex again, it has shifted 2 units to the left and then down 1 unit. So down 1 unit is -1. Remember, we put that at the end of our function. But because it moved left 2, we like to think -2, but it's actually +2. +2 is what we are going to put in our parentheses. So here we go. H of x is parentheses x plus 2 squared and then -1. Okay, when we reflect in the x-axis, it just makes your function negative. However, when we reflect in the y-axis, it makes your x variable itself within the function negative. All right, so with example 3, sorry, I had to think about it. It says the graph shown is a transformation of the graph of f of x equals x to the 4th. Find the equation of the function. So a general x to the 4th function, by the way, looks just like a parabola except it's kind of flattened in this area. But either way, it would have been more so like this as the original. Okay. However, it has been reflected in the x-axis because it reflected, I want to show you, it reflected this way, right, around the x-axis, okay? So it reflected in the x-axis, and not only that, it reflected and then it moved up 2 units. So this function should be g of x equals -x to the 4th, and that's because of the reflection, and then +2 because it shifted up 2 units. In our try 3, again, remember the parent function f of x equals x to the 4th would have been kind of like a flattened function right here. And then let's just describe what happened. Well, first of all, it flipped again in the x-axis. All right, so that makes that part negative. And then not only that, but its origin, if we want to call it an origin, not the origin, excuse me, but its vertex shifted to the right 1, 2, 3 units. Now, remember, if you go left or right, it's opposite of what you think. So it's not +3, but it is -3 that we're going to use. So this function should be h of x equals negative parentheses x minus 3 to the 4th power. And I don't put anything at the end because I have not shifted up or down. Okay, these are terrible graphs. I do apologize. They just didn't transfer very well. But anyways, it says for us to compare the graph of each function with the graph of the function below, state the domain. So the original graph of this function is the square root of x. And the square root of x, remember I said, is like lift off. So it starts at the origin and then it lifts off that direction. So how has it been transformed? So for this first function, what I see is that it has, instead of it going up, it is now going down. That's not a good color to use, so here we go. It has gone down on that function. Okay, so it reflected across the x-axis. So what we will say is that basically that it has been reflected. So this one here, oh my goodness, I'm trying to change markers. Okay, this one here has been reflected across the x-axis. Okay. All right. And it says state the domain. So the domain for us, notice it is a closed dot right here. So the domain, if I use interval notation, I would use a bracket, then a 0, and then it is continuous to positive infinity. Okay. Let's look at the next graph, the graph on the right. Okay, what has happened here is that instead of it being reflected, in the y-axis, it got reflected across the, in the x-axis, is now reflected in the y-axis. So, and we can see that because if I were to fold my line, if I was to fold my graph right along my y-axis, I would get a symmetric graph, okay? So this one has been reflected across the y-axis. And then our domain, if I use interval notation, it comes from negative infinity up to 0, and it's a bracket on 0 because it included that dot. Let's look at the next one. All right, we are to compare the graph of the function with the graph of the function below. So, and then we're going to state the domain. So again, let's take a look at what's happened. The first thing that I see is that it has been reflected across the x-axis, right? And then not only that, but it has been shifted once it got reflected, right? It looked like here. It then got shifted to the left 2 units. So we will say that k of x, which is the name of this function, so k of x has been reflected across the x-axis and shifted 2 units to the left. Okay, so the domain then for this problem is, if I use interval notation, it will be a bracket on -2, and then it is continuous thereafter to positive infinity. All right, so some more vocabulary. So non-rigid transformations. So horizontal and vertical shifts and reflections are called rigid transformation because the basic shape of the graph is unchanged. However, non-rigid transformations are those that cause a distortion or change in the shape to the original graph. Such transformations are a vertical stretch where a is greater than 1 and the function y equals a times f of x, and a vertical compression or shrink where a falls between 0 and 1. So in example 5, we're going to compare the graph of the function below with the graph of a parent absolute value function. Remember, the parent absolute value function is, for example, f of x equals the absolute value of x. And as a reminder, the absolute value of x starts at the origin, and it's kind of like the slope. This number in the front that you don't see is a 1. Its slope is telling you for whatever you do to one side, you do to the other side. So you go up 1, right 1, plot a point, up 1, right 1, plot another point. And then you're going to have the exact same on the opposite side. So that's the parent function. However, when I compare to this one, this new slope is 3. So yes, I'm still starting at the origin, but I'm going up 3. So 1, 2, 3 over 1, plot a point. 1, 2, 3 over 1, plot a point. So this one has been stretched by a factor of 3. So the way we will write that is the graph of h of x, which is the new one that we wrote. The graph of h of x has been stretched. I should say vertically stretched by a factor of 3. All right, so for try 5, we are to compare the graph of the function below with the graph of a parent absolute value function. We just saw the parent absolute value function on the other one. So again, we want to focus on the number that comes in front. So it's kind of like we're calling it a slope, but it's actually not. But we're going to mirror the image onto the other side. Again, this one does not have a vertical transformation, meaning it doesn't have like a plus or minus C, some plus or minus number at the end to shift it up or down. So its origin is at 0. And then it's telling me to move up 1 to the right 3, plot a point, up 1 and to the right 3, plot a point. So this one is pretty wide. I should have actually fully graphed it out, but this is a terrible stylus, so it's pretty hard to do. Either way, so this one is a vertical compression. So the graph of g of x has been compressed by a factor of 1/3. Just a reminder, compression and shrink are interchangeable words. Okay. However, compressed is only for slopes, if we want to call it that. Slopes that are between 0 and 1, and stretch are those that are numbers greater than 1. All right, so example 6, it says use a graphing calculator to compare g of x equals 5 times x squared minus 2 to the function of x squared. Describe the shifts and stretches. So for this function, the best thing I can say is to go ahead and type it into our graphing calculator. So remember to type it in your graphing calculator. You go to y equals, and you will type in 5 parentheses x squared minus 2, close your parentheses, and then graph it. I'm doing that now, by the way. So what I see is that this graph has been stretched by a factor of 5, which I pretty much could have decided that it was going to be stretched by a factor of 5. But it has been shifted down 10 units. Now, some of you are probably like, well, Ms. Richardson, I don't understand why it's been shifted down 10. I would have thought that it would have been to the right 2 because it's in parentheses. Well, if you were to distribute your 5, you would have gotten 5x squared minus 10. And so it perfectly describes that this function should be stretched by a factor of 5 and then shifted down 10 units. So I'm going to write that, stretched by a factor of 5 and shifted down 10 units. Okay, our last one is, again, it says to use a graphing calculator to compare. Now this one should be more so along what some of us may have thought on the last problem, or if you didn't, now hopefully you, having seen the last example, you've got it. The 5, again, tells us that it's been stretched by a factor of 5 and shifted down 2 units. And again, you should double check on your calculator to be sure that what I've written is accurate. But based off of the transformations, this should be accurate, okay? Either way, if you have any further questions, just come see me for tutoring.